Hello, this is Roger Hosking, and today we're going to take a look at some design strategies we've employed to take advantage of the Virtex-7 FPGA for our new family of software radio products. The Virtex-7 is actually part of a Series 7, which was announced by Xilinx. The Series 7 really has three different members. The first is the RTX, which is the lowest performance member of the family, equivalent to a Spartan 6. The Pentek, which is the mid-range performance member, and then the Virtex-7, which is the maximum performance of the three different members of the Series 7. So we've chosen to use the Virtex-7 to go into our next generation of software radio products. If you compare the Virtex 4, 5, 6, and 7, one of the metrics you can use is the number of logic cells. In this case, what we want to do is compare the number of logic cells in a given size package going through these various four generations of Xilinx parts. So what we're showing here in the graph is we're showing a Virtex 4 device available in different densities ranging from the LX40, which is the smaller density device, up to the LX160, which is the highest density device in that 35 millimeter package. And we can see that on the vertical scale we're showing the number of logic cells in thousands in that particular series of devices. Moving to the Virtex 5, we see a nice increase in terms of resources in that same size package. Moving to the Virtex 6, an even larger, more dramatic increase in terms of logic cells, and then finally the Virtex 7 with even more. So what we're saying then is that the reason that Xilinx was able to do this to achieve these higher densities was to shrink the cell geometry from 90 nanometers down to 28 nanometers. The other thing that Xilinx has done in the Virtex 7 is taken some steps to reduce the power dissipation for a given function, so that what they're claiming is half the power, meaning for a given function the Virtex 7 will dissipate half the power compared to the Virtex 6. Now let's take a look at some other comparisons between just the Virtex 6 and the Virtex 7. Here we're showing a bar graph that shows the maximum number of DSP slices in the largest Virtex 6 compared with the maximum number of DSP slices in the Virtex 7. This is arranged in a 0 to 100% normalized scale, so you can see the comparison between the Virtex 6 and Virtex 7. The second parameter is the maximum speed of the gigabit serial rate interfaces on the two different families. Again, a much higher serial clock speed on the Virtex 7. This shows the number of logic cells. This shows the number of bits of block RAM, which is very important for making up structures like RAM tables and FIFOs and so forth inside the FPGA. This bar graph shows a twofold improvement in the speed of the PCI Express native interface inside the FPGA, because we're going to Gen 3 on the Virtex 7, which doubles the rate for a by-8 interface to 8 gigabytes per second. The number of configurable logic blocks has also shown a big improvement. Now let's compare the power performance on the Virtex 6 and Virtex 7. The first metric is relative I/O power. This is the power that it takes to drive an I/O pin. And here you can see that the Virtex 7 benefits from a 30% reduction in I/O power compared to the Virtex 6. The dynamic power is the power it takes to switch a cell, having to do with the capacitance of a cell when it changes state. Here we see a reduction of 25% in the Virtex 7. The last metric is the static power. This is the leakage current, the power that's dissipated even when the device isn't clocking. And here, the Virtex 7 achieves a dramatic 65% reduction compared to the Virtex 6. What Xilinx is claiming is that a weighted average of these different metrics comes out to about half for the total power for a given function relative to the Virtex 6. So what we've done is taken this major step in improvement in FPGA, and we are introducing it as part of our new series of Onyx Virtex-7 software radio modules. We're targeting radar, communications, and data acquisition applications. It is a strategic extension of our very popular Virtex-7 Cobalt product line, introduced in December of 2009, with shipments occurring now for over 2.5 years, our most successful product ever. The Virtex-7 enhances the power of the software radio module through its greater resources and greater speeds, but we've also taken advantage of all of the front ends that the Cobalt or the Virtex-6 product had. So immediately the Onyx has a wide range of different front ends that will suit a lot of different applications. We've doubled speeds of both the interface for the PCI Express and the memory, and there's an easy migration path from the Cobalt to the Onyx. We're offering the XMC module that you see here as the basic building block, but this block also is available in PCI Express, Compact PCI, and VPX form factors, as we'll see later. The way we construct both Cobalt and Onyx is in a modular fashion, where the main board that you see here contains the FPGA. It contains the XMC connectors here and here for gigabit serial connections to a carrier or to a single board computer. You see the I/O connectors for general purpose user I/O here. The front end module contains A to Ds and D to A converters of different quantities and speeds. That front end module attaches to the main board and now forms the personality of the end product that we ship to our customers. We surround everything with a metal shield depending on the type of cooling and the type of package it's in to do electrostatic shielding and thermal management. If we take a look at the predecessor product, the Cobalt Virtex-6, this shows the main board, the larger board with the FPGA on it, and this shows one of the front-end modules, one of the A to D, D to A cards. In this case, we're looking at a 4-channel, 200 megahertz, 16-bit A to D converter. What we're doing going forward into the Virtex-7 is we're keeping that front-end module with the A to Ds, but we're replacing the Cobalt Virtex-6 with the new Onyx Virtex-7, which you see here. We're going to go into first some more details about what's on the new Onyx main board. First of all, as we've seen, the FPGA resources are a major benefit. What we have compared to the Virtex-6, which you can see here in terms of logic cells and DSP slices, we have in the members of the Virtex-7 FPGA, we have increased the number of resources beyond the largest member of the Virtex-6 family in the 485T and the 690T, a major jump. If we compare different families of the Virtex-6 and Virtex-7, you will find that they will have a mix or ratio of DSP functions for signal processing and logic cells for logical functions. In the case of the Virtex-6, Xilinx came out with the LX family, the Virtex-6, that emphasized logic resources, and they came out with the SX family, which emphasized DSP resources. In the Virtex-7, there is only one family. It's the VX family, and it's a mixture of the DSP and logic mix. And you can see how the Virtex-6 and Virtex-7 compare on this particular chart to show the number of resources in each of the specific devices that we're talking about. Now, when you're choosing the FPGA that you need, you obviously would like to spend the least amount of money to get the logic cell requirement that you need, or the number of DSP slices that you need. So let's look at relative pricing of the different Virtex-6 members plotted against the number of logic cells in those devices. And now let's take a look at the Virtex-7 price versus logic cells. These prices are the pre-production prices. We expect in production these prices will come down to about here. In this case, what you would do for the simpler applications, you would choose the Virtex-6 as a more economical package. When you have a heavy-duty application, you can migrate up through to the Virtex-7. Let's take a look at the same kind of chart for DSP resources. Here we see the price per DSP slice, if you want, on the Virtex-6 family, and we're going to show the same kind of plot for the Virtex-7 devices with an expected reduction in prices to these levels. Again, what you do for the simpler functions, you would choose the LX130, migrate on up through the 690, which is the highest performance Virtex-7. Notice that in both of these two slides, the SX475T is no longer an economically viable solution. In fact, the 485T has replaced it in terms of a better deal for getting both DSP resources and for logic cells. For the reasons that you see on these charts, we're going to keep offering the Virtex-6 family, the Cobalt family, as a parallel product family to the Virtex-7 Onyx, so you can choose which device you need to handle the different requirements of your application, from the very simple to the very complex. If we now take a look at the memory resources on the board, the Cobalt had a maximum memory size of 2 gigabytes with a 800 megahertz transfer speed. What we've done on the Onyx, the Virtex-7, is we've doubled the size of memory to 4 gigabytes, and we've doubled the transfer rate to 1600 mega transfers per second. On each of those 32-bit lines, you can transfer 3200 32-bit words, 1600 mega transfers per second on those lines. We take a look at the PCI Gen 3 interface, comparing the Virtex-6, which has only PCI Express Gen 2. A by 8 interface gives you a 4 gigabyte per second peak rate. The Virtex-7 doubles that, now going to Gen 3 to 8 gigabytes per second. Significant improvement, and essential for the very high speed transfers that some of the very fast A to D converter front ends we have will require. In terms of A to D performance, here's a plot that shows the spectral purity of a 70 megahertz sine wave signal sampled at a 200 megahertz sample rate clock. And you can see that the maximum spurious signal is just a little under 90 dB. In fact, the TI specification for this A to D converter is 88 dBc. So what we're showing here is that we have preserved the manufacturer's specification of signal purity for these A to D converters, even though we're putting 4 of these in a very dense, small form factor, very close to heavy-duty digital circuitry. And we've done that with some very careful shielding, board layout, voltage regulation, and filtering. And we're quite proud of our performance, our analog performance, in regards to these front ends. Likewise, with a D2A converter, where we're sampling at 800 megahertz and generating a 70 megahertz sine wave out, again, we're preserving the manufacturer's specifications for signal purity by using the same design techniques. We've added several very nice resources to the Virtex-7 Onyx board. We have 10 onboard temperature sensors. These are very useful during development because these boards are being used in air-cooled, conduction-cooled, 3U, 6U, on carrier boards, on single boards computers, in a lot of different form factors. And it's very important during development to make sure that the cooling strategies and thermal management solutions that you come up with in your design of your system will result in suitable temperatures on the board. We also have installed 9 onboard voltmeters to measure the critical power supplies that are developed for the specific resources of different devices on the board. New to the Onyx is the 2 onboard ammeters that measure both the 12 volt and the 3.3 volt supply currents that are used by the board. This way you can measure the total power directly that's going into the board. This will help you for thermal management, to do planning for your cooling, and it will also help you to plan for your power supply requirements. All of these meters are equipped with threshold detectors that you can set for certain alarm points, so that if the limit is exceeded, you can get an interrupt back to your system. These resources are very useful not only during development, but can also be delivered through to your end customer as a power-on self-test to monitor the health at power-on, and also during runtime for an ongoing health monitoring facility that you can incorporate in the final runtime application. Customers are usually quite interested and very impressed when you can do such a good job. The other thing that we've done is install power management circuits that allow you to shut down power to unused components. For example, if you have 4 A to D converters and you're only using 2, you can shut power down to the 2 unused A to D converters to save power on the board. In terms of the PCI Express configuration, we have the PCI Express engine itself is inside the FPGA. So it does lead to some challenges for configuration of the FPGA. The first challenge is when you turn power on to your system, a process called enumeration takes place where the host discovers all of the PCI Express endpoints. Large FPGAs take a long time to configure, so sometimes for a large FPGA the enumeration is missed and you need to do a soft boot to rescan the system to find the board. The second is that the parameters that are assigned to the FPGA-based PCI Express endpoint can be lost if you reconfigure the FPGA and wipe them out. A third problem is trying to reprogram the FPGA across the PCI Express interface itself, because this can destroy the PCI Express interface that's being used to deliver the new image. So we're going to address each of these 3 issues with a new resource which we call the Onyx PCI Express Configuration Manager block, which you see in the middle. What it does for power-up is it presents a temporary PCI Express endpoint, a very simple endpoint immediately on power-up, so that the host computer can see the board, pass it parameters so that it's now enumerated in the system. Those parameters are temporarily stored in the configuration manager. After the large FPGA is fully configured, then those parameters are passed over into the large FPGA and the board can continue operating without having to do a restart or reboot. In the case that the board has come up with the, let's say, flash application number 1 as a bit stream on the initial power-up, and you want to change the FPGA configuration to use a new flash image of the bitstream application number 2, what we can do is automatically save the configuration space parameters down in the configuration manager block. We then can load the new flash application up into the FPGA, completely replacing every part of the FPGA, and then move the parameters back up to restore the configuration space parameters for the PCI Express interface in the new image. So this is all done under software control, and no reboot or restart is needed to switch between flash applications. The last challenge is to be able to reload the FPGA itself across the PCI Express interface. Here, in this case, what we're doing is taking advantage of the small PCI Express interface in the configuration manager, and as a software application, what we can do is we can first store the parameters, the configuration space parameters from the large FPGA. We can then load the new host bit stream up into the new FPGA, completely replace every cell in the FPGA, and then when we're finished, we can restore the parameters up into the FPGA, all automatically, all with a simple software command, all controlled exclusively through that PCI Express interface without the need for JTAG cables, without the need to reboot the system. This is very important during development because it simplifies loading new images as you test new images. It can be also very useful for runtime because you can reconfigure the system during operation during runtime while the system is deployed without having to restart or reboot the system. It's also important because you can load the FPGA without having any non-volatile image stored in a flash memory. This is very important in case that the IP bit stream is a sensitive application and needs to be secured. Now let's take a look at the different front ends that are available for both Cobalt and Onyx. We saw before how they can be attached quite easily. So in this case, this is the first product we looked at. This is the 4-channel 16-bit 200 megahertz A to D converter. If we remove the front end and instead put on a different front end, we now have the 730. This is a 1 gigahertz 12-bit A to D and a 1 gigahertz 16-bit D to A converter. A very nice transceiver function for signal bandwidths up to about 400 megahertz, suitable both for radar and for communications transceivers applications. Going up even higher in frequency, we can attach a new front end and now have the 740, which is a 3.6 gigahertz 12-bit A to D converter. It can also be used as a dual-channel 1.8 gigahertz 12-bit A to D converter simply by throwing a software switch. This module then in the single-channel mode can directly digitize a 1.5 gigahertz bandwidth signal directly with a single A to D converter. The DDR3 memories are fast enough to buffer and hold the data for transient capture for radar applications, and also to buffer data as an elastic store in the case that you are sending it out across the PCI Express interface. The 750 brings two 12-bit 500 megahertz A to D converters and two 16-bit 800 megahertz D to A converters. So here we have a 2-channel transceiver with bandwidths of 200 megahertz. We can also drop the sample rate of that previous product to 400 megahertz from 500, and now we gain an extra 2 bits of resolution, so we have dual 400 megahertz 14-bit A to D converters. We keep the same two 800 megahertz 16-bit D to A channels that we had before. For people who need the maximum number of analog outputs, the 770 features 4 1.25 gigahertz 16-bit D to A converters, each equipped with a digital up converter that accepts IQ baseband 32-bit complex samples, does the frequency translation up to IF frequencies anywhere up to 625 megahertz. The bandwidth of the baseband signals that are translated up can be as high as 250 megahertz bandwidth. And there are a total of 4 parallel channels running in this particular product. This is extremely useful for transmit beamforming applications for arrays that are for radar arrays or communications arrays. The 790 incorporates an analog integrated tuner that it has a programmable gain low noise amplifier, a VCO programmable between 925 and 2175 megahertz, and a complex analog mixer that will allow you to frequency translate a signal in the 925 to 2175 megahertz band right down to DC, and then the baseband I and Q components are filtered with 2 low-pass filters programmable from 4 to 40 megahertz as the cutoff frequency. The output of the IQ baseband signals are then digitized with 2 200 megahertz A to D converters. This gives you a complete tuner, L-band tuner, that is capable of accepting the coaxial signal feed coming down from an antenna mast, where the ultimate antenna frequency after conversion down to L-band could be at much higher frequencies, K-band, S-band, and so forth. The 711 is a quad serial FPDP module that instead of having analog inputs has digital inputs. These can be either over copper cables or over optical cables using either single mode or multi-mode fiber. The data rates range from just over 1 gigabit per second to over 4.25 gigabaud. For example, at the 2.5, which is a popular frequency, each of those channels can sustain a 247 megabyte per second transfer rate in both directions. This product is extremely useful for connecting multiple chassis together or racks, equipment racks together, where you need high-speed interconnect, digital interconnect cables, or for connecting the remote acquisition systems that might be an A to D converter that could be up on an antenna mast, where the digital data can be fed down through a copper or optical link down into your signal processing system that could be then attached with this product. The Model 720 is a very nice general purpose product that features 3 200 megahertz 16-bit A to D converters and 2 800 megahertz 16-bit D to A converters. This gives you a 80 megahertz bandwidth transceiver function, 3 channels in, 2 channels out, and we want to use this product to illustrate the timing signal generator, the timing functions that are built into these products. We feature a programmable voltage-controlled crystal oscillator. This is a new class of device that has very low phase noise, low jitter, and programmable in frequency with 32 bits of resolution. This signal can be used as the source for the sample clocks for the A to Ds and D to As. We run the signal from the VCXO through 2 dividers that are programmable, and in the case that you perhaps need a 800 megahertz D to A converter clock and a 200 megahertz A to D converter clock, you can program the frequency of the VCXO to 800 megahertz, divide it by 1 for the D to A, and divide it by 4 for the A to D. Now you have a completely synchronous A to D, D to A system, all driven synchronously from that single VCXO. Instead of the VCXO, however, you can substitute an external sample clock as the input. In this case, maybe an 800 megahertz external sample clock. We also allow you to deliver the external clock using a differential low voltage PCle timing bus that comes over a front panel ribbon cable. This is used for synchronization of multiple boards. Lastly, we accept a 10 megahertz system reference that allows you to phase lock the internal VCXO to your 10 megahertz system reference. Effectively, what you have is a programmable frequency synthesizer built right into the product. In terms of multi-board synchronization, using a simple ribbon cable, you can synchronize up to 4 of these boards together just by connecting that cable. If you need more than 4 boards, we have dozens of other clock synthesizer and synchronization products. For example, this one is a PCI Express board that generates 8 of these ribbon cable low voltage PCle timing signals to synchronize as many as 8 different modules. If you have more than 8, we have a 1U rack mount synthesizer, the 9193, that generates up to 15 of those ribbon cable signals. We allow you to generate D2A waveforms extremely easily. Here what we're seeing is we're seeing 4 different waveforms loaded in different locations of memory. Each of these waveforms represents a sequence of samples that has a particular characteristic or waveform. But how do you get these waveforms to play out through the D2A converter easily? To answer that question, we've provided a D2A waveform generation system that uses a linked list. This is an engine that reads the directions, the script, that you enter in parameters in each link of the list. For example, in link 1, we specify a waveform with a delay of 7 from the trigger, a length of 24, repeated 3 times. The RAM location in memory is shown here. And then we continue after the operation to another link, link 3. So when we play the first link, what we get is that first waveform stored at that address that we've specified, repeated 3 times with the delay that we've specified. Link 3 specifies a different waveform with a different delay, a different length, and a different location in memory. So when the first link is played, it automatically chains to link 3, and we play out that link. When that is finished, we go to link number 4, we play out its waveform and parameters, and then we link to 2, and finally we play that. So each of these different sequences can be conditioned with a trigger or not, depending on the setting of the continue bit, another parameter in the list. There are up to 64 different list entries that you can have with different links, with different waveforms, different combinations of delays and triggers and so forth, so that you can create some extremely complex waveforms simply by filling out the parameters of the table, loading the waveforms in memory, and then kicking it off either with a hardware or a software trigger without having to do any FPGA development. This is all supported with just simple software. We have a very similar concept with the A to D acquisition. So again, we have a linked list that allows you to specify the acquisition start from a delay from a trigger, the length of the acquisition time, the number of repeat cycles that you want that to occur, and then finally, where do you want to do, what do you want to do after you do that? And again, the linked list table allows you to choose up to 64 different acquisition scenarios. When you acquire the data can be sent directly across PCI Express to memory, or we can buffer it in local memory on board and then send it out across through a DMA transfer to the host computer. This allows you to take advantage of the memory to achieve an elastic storage for buffering data. The other thing that many of our customers like, who are specifically interested in time tagging or time stamping the data, is to take advantage of our metadata generator. If you apply a 1 PPS clock that comes typically from a GPS card, we start a series of counters that will be trapped at the time the trigger occurs to a certain count. Those count values are transferred into a set of registers, and when the data from the memory is sent out into the system, we also append a packet that is just this header information. The metadata gets appended to uniquely identify every parameter of capture, the number of clock ticks from the last PPS clock, the offset, the trigger number, the gate, the channel number, and so forth, all gets identifying information appended right to the data packet so that it can be identified when it's retrieved by the system. In terms of model numbering and form factors, the first 2 digits of our model number determines the form factor. 7-1 indicates XMC. This is the basic building block for Onyx and for Cobalt. The next 2 digits determine a 3U or 6U compact PCI form factor. These are achieved through carrier cards that accept the XMC module and then allow you to plug these modules into either 3U or 6U compact PCI chassis. We also have 3 different carrier cards for PCI Express. So these boards can plug right into a motherboard, a server motherboard, a desktop PC. This is a very low-cost development environment for software and for FPGA development. It's a very good way to start your project. Later on, when you're ready to deploy it into a severe environment system, for example, you can choose the 53 as the 3U VPX form factor. Again, another carrier board. This can be conduction cooled. This is suitable for some very, very extreme environments. The last digit in the part number is reserved for additional IP that we can install at the factory to make the board even more have even more functions than it does than the ones we've already seen. For example, the 71760, that's the 4-channel 200 megahertz A to D board, can be changed and upgraded to the 761 with 4 digital down converter IP cores and a beamform summation engine. We're going to look at just this one as an example. Here on the left you see the 4 A to D converters kind of redrawn, but with a large block for the FPGA shown here in yellow. The 761 core includes 4 digital down converters, each programmable in decimation from 2 to 64K to give you output bandwidths from 80 megahertz down to a few kilohertz, and each one, of course, programmable in tuning frequency from DC to 100 megahertz. So it's perfect for down converting IF signals. You can source each of the digital down converters from any of the 4 A to D converters. So there's a lot of flexibility in terms of assigning digital down converters to your antennas. The output of the digital down converters is complex IQ baseband data. This data is sent into a power meter and threshold detector where we calculate I squared plus Q squared to actually calculate the power. The threshold detector allows you to set a threshold so that if the power exceeds that threshold, you get an automatic interrupt to your system. This is extremely useful for monitoring or scanning applications where the power detection is done locally in hardware right inside the module, saving the CPU card or your system host from having to do a scan and perhaps miss something. We also have added a beamforming summation block that sums I and Q on each of the 4 digital down converter outputs, and we've provided a method for propagating the sum from one board to another. So this Aurora 4X port that uses the P16 connector can accept a sum from a previous module. We add the 4 channels locally to that sum, create a new sum, and propagate it out through the second Aurora 4X port to the next module. Aurora is Xilinx's link layer protocol. It's a very efficient, very easy to use gigabit serial link that's extremely suitable. This allows you to cascade any number of modules in out until you have the number of antennas that you need for your beamform system. So we have another IP core which is called the 762, which includes 32 digital down converters instead. The 720, this is a new main board, has a 721, which adds, again, down converters, beamformers, and interpolation. This then is a list of all the different Onyx products that are available and showing you the different resources that are available. In order to program the Onyx family, we offer a product called ReadyFlow. It's a board support package that includes high-level C callable library functions, and it also has drivers for Windows, Linux, and VxWorks operating systems. All these functions are tested, validated. We provide full source code with these products and lots of examples to help you get started. Another nice resource that we include as 2 utilities with the ReadyFlow package is the signal viewer. And the signal viewer allows you to look at live signals coming out of the Pentek modules, either from the A to D converter or from the digital down converter on any of the channels, to look at the time and frequency domain characteristics of those signals. It's a fully instrumented virtual oscilloscope, virtual spectrum analyzer that you can pan, zoom, do frequency analysis and calculation. Harmonic distortion windows are provided as well. Amplitude and frequency are shown in their separate windows. So in addition to that, we've added a command line engine. What this allows you to do is it pops up a command line window that accepts commands that are the parameter name and then the parameter value. After you enter a string of commands that include names and values and hit carriage return, those values are then programmed into the board automatically by this small application, so you can have an immediate effect in real time on the performance of the board, and after you make that change you can see the effect on the signal viewer because it's a live signal. So what these two resources allow you to do is within 15 minutes of opening the box, you can have the board up and running, connect up your own signals to the board, look at those signals in time and frequency domain, and then change parameters for tuning and bandwidth and so forth without having to do any software programming. It's an extremely easy way to get started and to validate the operation of the board. For customers who want to extend the FPGA design by adding IP or adding algorithms to the FPGA, we offer our GateFlow FPGA design kit. It works in conjunction with the Xilinx ISE Foundation package. We include full VHDL source code. We include test benches and standardized interfaces for the memory, the A to Ds, PCI Express, and clocking. So what we're going to do is take a look here at a kind of a representational view of these interfaces that we provide. You can see surrounding the center block are all of the low-level arms and legs of the board, the memory controllers, the PCI Express interface, and the A to D interfaces. Inside this user application container, we have installed the standard factory modules, the data formatting, the waveform generator, the acquisition engine, the metadata generator. All of these are example modules that we've installed and connected up, and those modules can be removed, can be replaced. You can put different functions in the signal path to and from these modules so that after you make that change, you can recompile the project, keep all of the parts of it that you want to preserve, recompile it, and you'll have a very low-risk path for achieving custom FPGA design. This is a list of markets and applications that we're addressing with the Onyx family. Most of these are high-performance government, military, aerospace applications. As you can see, these products are generally highly effective for both radar and communications applications. If you go to our website, you can get a lot more information about Onyx. You can see typically a featured product on the front page. You can also register to get a short email to update you whenever we release new information or new products on the Virtex-7. But one of the best ways to find a product once you're interested in selecting one is to go to our product selector. This is a tool. When you first open up the tool, you see a list of parameters on top, and then down below you see a list of products. In the opening screen you'll see 250 or 280 products. When you start selecting parameters, for example, if you pull down the selection list to PMC and you have 2 channels of A to D and you have a sampling rate of 200 megahertz, for example, that list will begin to shrink. And as you select more parameters that you care about, you will get a shorter and shorter list. So at the end, you will then have just the products that meet the selection criteria that you've chosen. It gives you a very good way to see all the products that meet your requirements and exclude those that don't. So what we've seen is that the Virtex-7 Onyx is a strategic extension of our most successful Virtex-6 Cobalt product line. Pentek was the first in the marketplace to introduce the Virtex-6 XMC module. We were the first to ship. We began shipping in the spring of 2010. We are the first to announce the Virtex-7 software radio module, and shipments are commencing right now. The product is available in XMC, PCI Express, Compact PCI, and VPX. We're taking advantage of the Virtex-7 FPGA to boost the DSP processing resources and to reduce power. But we're also pulling forward all of the Cobalt front ends for the A to Ds, D to As, and so forth that you've seen in the last few slides. PCI Express Gen 3 will double your PCI Express interface to 8 gigabytes per second. We're doubling the speed and the density of the DDR3 SD RAM. We've added that powerful PCI Express configuration manager to make it very easy for you to handle the issues with configuring the FPGA and even loading a new image directly across the PCI Express interface itself. The voltage, temperature, and current monitors make it extremely easy for you to monitor the health of the board and to include that in your end user application. There's a easy software, hardware, and FPGA migration path from Cobalt to Onyx. This is a list that shows all of the different Cobalt, which is the leftmost list, and the Onyx, which is just to the right of it, showing you the parallel product lines with the key resources that are available for each. Notice the difference between Cobalt and Onyx is simply in the third digit of the model number. Now let's take a few questions here. Let's see, the first question. What are the most common applications you've seen from customers using your products? So as I've said, the communications and radar are really characterize the applications that we see mostly. We're typically moving towards higher and higher signal bandwidths and higher signal processing requirements in those domains. A lot of our customers take advantage of the triggered operation for radar applications, and they take advantage of the multi-channel synchronization for phased arrays and multi antenna applications, both in radar and in communications. Our beamforming IP makes the operation of beamforming quite easy. Next question. Do they generally do processing in software or on the host or in hardware in the FPGA? So we have obviously it's a mixture. The higher, I guess the more compute-intensive applications are often done in the FPGA itself. In fact, we sell about 80% of our customers the FPGA design kit with the intention that they're going to add their own IP to the FPGA, and we are extremely good at supporting that activity. For the lower speed signal processing requirements, typically it's easier to do it on the host computer. So the answer is some of each. The next question. We want to know if you offer a standalone Onyx board. I think by that question what you mean is a board without an A to D and D to A converter or any front end. And the answer is yes, and we are actually coming out with another product, which will be the 610 and 710, which you can see at the very bottom of this list. And that will be a very simple digital I/O, which could also be used as just a FPGA processing engine with a very high-speed PCI Express link into the rest of your system. So it could be used either with the digital I/O or just as a co-processing engine to the rest of your system. What are some new front ends that? Okay, I understand. We are obviously going to extend the number of different A to Ds and D to A converters and software radio functions by adding new front end boards, and these boards will be taking advantage of the latest devices we can find in the industry. One of the things we'd like to do is to have a complementary product to the 3.6 gigahertz A to D converter and have a 3 to 4 gigahertz D to A converter, so we can have a transceiver with those very high sample rates. The other thing is we'd like to have a higher density 500 megahertz A to D converter, say up to 4 channels. We're looking at possibly going to an 8-channel 200 megahertz A to D converter. These are some products that are currently under discussion and evaluation. If you have any special requirements, we'd be glad to discuss those with you as well. I think this covers all the questions that we've had today. I really appreciate your time and attention. Please give us a call at Pentek. Go to our website, find out more about our products. We have worldwide product support and distribution and we'd love to discuss your application with you. Again, thank you so much for your time today.